In this section, we're going to talk about how to calculate the length of the curves that we're getting here from these vector valued functions, and that is also called arc length. You may remember that we did arc length back in Calculus 2. The difference now is our curve is not represented by a rectangular function with x and y. It's actually represented by a vector valued function, and it could have three components. So this could be a three-dimensional curve, but the formula we're going to use to find this arc length is still really similar. So if C is a smooth curve given by r of t equals x of ti plus y of tj plus z of tk on an interval a to b, then the arc length of C on the interval is given by the following formula. So arc length is very commonly represented by a lowercase s. We're going to have the integral from a to b because we need a specific starting and ending point to find the length for. Our integrand is the square root of x prime of t squared plus y prime of t squared plus z prime of t squared dt. Well, if you notice, x prime, y prime, z prime, that is just the components of the r prime function. And anytime we square our components and add them together under a square root, that is considered to be a magnitude. So really, all we have inside this, this integral is the magnitude of r prime of t. Sorry. There we go. So this is equal to the integral from a to b of the magnitude of r prime of t dt. So it's pretty simple and straightforward. Let's try a couple of examples. We want to find the arc length of the curve represented by r of t equals 3ti plus 2 cosine tj plus 2 sine tk on the interval 0 to 4 pi. So these t values here look like angles in radians because our t appears multiple times inside of a trig function. So that's pretty common. If all of the functions were algebraic, you might just have two nice whole numbers there. So we need r prime of t, which is 3i minus 2 sine tj plus 2 cosine t k. And arc length is going to be the integral from 0 to 4 pi of the square root of the magnitude of our r prime of t. So we're going to square each of those component functions and add them together under a square root. And at first glance, this looks like it may be a pretty difficult integral to calculate. You're always welcome to type these definite integrals into your calculator for help calculating them, but this one's actually going to work out pretty nicely. This is 9 plus 4 sine squared t plus 4 cosine squared t. And for these two terms, if we factor the 4 out, we have sine squared t plus cosine squared t, which is an identity that's equal to 1. So really, everything behind this point is just 4 times 1, which is 4. So we've got that 9 in the front, and then when we simplified the back, it just turned out to be a 4. So we're just integrating a constant here. We're just integrating the square root of 13. And with respect to t, that would be square root of 13t from 0 to 4 pi, which would be 4 pi root 13 minus 0. So for an exact answer, we could say 4 pi root 13. Or for an approximate answer, we could type this into our calculator, get a better idea of exactly how long this is. Sometimes when we have those irrational numbers in there, it's hard to tell how long our path really is. And it's about 45.3 units long, and that would be our approximate answer. Let's try one more really quick. A golf ball is hit from ground level with an initial velocity of 120 feet per second at an angle of 30 degrees. You're going to find the length of the path of the golf ball. So this kind of ties together the projectile motion that we learned in the last section. So we're going to have to set this vector valued function up by ourselves. R of t is initial velocity times cosine of the angle. So we have 120 cosine 30 degrees t. And then because we're in feet, g is going to be negative 32. So we get negative 16t squared plus 120 sine of 30 degrees t. And it's hit from ground level, so there's no initial height. So that's our j component. We could simplify these trig values because they don't have any unknowns, and we could take our derivative. But if you think about it, our final answer needs to be the length of the path, which is arc length. And arc length is a definite integral. We have to have a starting point or a starting time and an ending time. So we could assume that the time starts at 0, but we don't know an ending time. So really what we need to do first is we need to figure out when this ball is going to hit the ground. So we need to take our y of t function, which is negative 16t squared, and then sine of 30 is 1/2, so this is just going to be plus 60t, and we want to know when that's equal to 0. Well, if you factor a t out, we get negative 16t plus 60 equals 0, and you could set them each equal to 0 individually. And we already knew that it starts from ground level. If we solve that second factor for t, it'll tell us when it hits the ground after the flight. And I get about exactly 3.75 seconds. So now we know what we need to integrate between 0 and 3.75. 0 is the start of the ball's path, 3.75 is the ending time of the ball's flight path. And remember, we are integrating the magnitude of r prime of t. So we need the square root of the derivative of our r of t function. Cosine of 30 degrees is radical 3 over 2, but I'm just going to go ahead and simplify that to a decimal. And I've got about 104. So this really is just 104t. Its derivative is just 104. For my second component, the derivative of negative 16t squared is going to be negative 32t. And the derivative of 120 sine 30 degrees t is just 120 sine 30, which we've already said is 60. So we need to try to simplify this as much as possible, see if we can work this out by hand. It's possible that we're not going to be able to. So 104 squared is 10,816. In order to square negative 32t plus 60, we technically need to write it twice and FOIL it. And when we do that, might need to make this a little bit longer. When we do that, I get 1,000 and 1,024t squared minus 3,840t plus 3,600. And we do have one set of like terms there that we could put together. That's going to be 14,416. Now, you don't need to waste a whole bunch of time trying to figure out if we could simplify this further. Your graphing calculator can calculate definite integrals. If you use math option 9, and option 9 says FNINT, which is function integration. If your calculator's fairly new, then it uses math type, and it will actually pull up an integral symbol, and you can fill in all the blanks that you need. If your calculator's a little bit older, all it's going to do is open up a set of parentheses, and you have to know the exact order of what to type in there. So the first thing you type in is your integrand. And then it wants to know what variable it is integrating with respect to, and we always just use x on the calculator. And then it wants your lower bound and your upper bound. So we could just have the calculator figure this out for us. And when I enter this into the calculator, I'm getting about 411 feet. Now there is a way that we could possibly check this. Remember the projectile, the path of a projectile. We're hitting from ground level. What we've calculated this time is actually the length of the path of the ball. So a similar value to that might be just range. We figured out the range of the ball. we would expect the arc length to come out larger, because remember, the shortest distance between 2 points is always a straight line. So when we follow that curve, it's going to be a little bit longer. But if we want to, we could just confirm that this answer is reasonable. I know the ball lands after 3.75 seconds, so we could calculate x of 3.75 and see if it comes somewhere in the similar ballpark. So the x function was 120 cosine 30t. Cosine of 30 we said was radical 3 over 2. So that's about 104t. So we want to calculate 104 times our t value is 3.75. And it definitely does come out very similar. I get 390 feet. So the range of this projectile is 390 feet. That is just the straight line distance from start to finish. But the curved path of the ball is 411 feet. So I feel much more confident in this answer because I see that my range is a similar value, and I know I expect the curved path to come out longer.